I'm going to talk about robot simulation. Basically, we'll talk about why we need some simulation, a kind of an overview of different ways of modeling a robot. Um, also, uh, kind of an overview and introduction of how to set up your robot in PyBullet. Um, there is more to it, but this is going to be an introduction video. Let me know in the comments if you have any questions. So, robot simulation. Let's talk about it. Obviously, uh, as I said, why do we need to simulate robots? Because, first of all, uh, when you have an idea, you want to bring it into life. Simulating it, it's going to make you test different scenarios. First of all, make sure your robot works before you actually build it, because there is so many details that you have to keep in mind when building a robot. And by simulating it, you kind of figure out the bugs within the robot, the things that go together and do not go together. Uh, and you realize, what can go wrong or not. Here, it's interesting. Obviously, you can make a robot simulation like this one. This is a spring mass simulation, and this is, the after they come to life. Um, so you see how similar they move in simulation and robot. Obviously, as the robot gets more advanced, you are going to need, obviously more details, more trial and errors. In simulation, it's simpler to test your idea on a simulation than on a physical model. Uh, you know, uh, so one of the things that you are going to need is a physics simulator that kind of simulates the laws of physics and how the robot will, you know, react basically or behave in a simulated environment. Um, so one of the ways of modeling a robot is the spring mass modeling, spring mass simulation. Um, so basically, a spring mass is a set of uh, basic interaction and integration loops. You you have some point masses which do not have any volume, and you also have these point masses have mass, position, velocity, and acceleration. The only thing that doesn't have is volume. On the other hand, you have springs that connect these point masses. These springs are also massless. They do have volume, but they don't have mass. They do connect two masses and have a rest length and stiffness that determines, how easily it, opens and closes. Um, this is an example of a spring mass robot. As you can see, these orange balls are the mass points or point masses that are connected with these blue springs that do not have a mass of their own. You can add masses and you can expand um, your object or whatever you're simulating as needed. One of the things you have to, in every simulator, you need to consider a time step. We call it DT. It shouldn't be larger than a millisecond, and you need to Also set a global time variable that start at 0. At each time step, you basically add dt to the global time variable, which is t, the big T. You also have an interaction step. What you do is compute all the forces that are acting on each mass from springs that are connected to that particular mass. And then you add any external forces on the mass, like gravity, collision, drag, friction, and all of that. And then after that, you integrate in the next step, which basically you update the acceleration and velocity and position each mass using Newton's laws of motion. Um, so the overall force that are applied to a particular point mass, we refer to it as F, which is the result of all the forces applied to that. Um, so to set up your data structure, you have a mass that you denote with m, and it's a scalar variable. And then you have a position p, it's a 3D vector. You have a velocity v, which is also a 3D vector in all this, the three different directions. You have an acceleration, small a, another 3D vector, and you also have external forces in the three different main directions, that also a 3D vector. For the spring, you have a rest length, L naught, it's a scalar. And you also have a spring constant K, which is also another scalar, which is equal to E times A divided by L for bars. And we have indices for two masses, M1 and M2. For the time increment, the t equals t plus dt. That you need to set it up first. And then you have the interaction step. For all the springs, you calculate the compression extension using F equals K times L minus L naught, which is the initial length. At each point in time, the force is calculated by this formula. You have the spring constant times the current length minus the L naught. For all the masses, you update the forces on each mass at each time step, and then you add gravity, collision, external forces, friction, and then you do the integration step, which is you calculate A, which is basically the force, the acceleration equals force divided by the mass. And you update the V, the velocity, by having the current V, the current velocity plus dt times acceleration. And then you update the position by having the current position plus V, the velocity times dt, until it reaches equilibrium. Or just keep continuing doing the steps. The time increment we talked about. We talked about different things. Now calculate if mass is fixed, we set v equals 0 at the beginning, right? If dampening, then you reduce v by multiplying the velocity times 0.999. And if colliding with ground, apply resisting force. And then that's for V, which is consequently is going to affect the position P. And then you repeat P forever. So here it looks like it doesn't have dampening, because when it hits the ground, it goes back up to the same height that was in the beginning. So looks like the dampening, or it's too small to, visually see it. Now, how to handle collision with the ground? You apply a ground reaction force, which is upward, once a node goes below ground, which has to be its z coordinate has to be less than 0. This upward force F sub g equals 0 for the x in the x direction and y in the y direction. In the z direction is minus z times k sub g. K sub g would be the spring coefficient of the ground. So it could be like 1,000, 100,000. The harder the surface is, the k sub g is going to be larger. Here's an example of bouncing object off the ground. Here is an actual human-shaped robot that is built using the spring mass model. Inside of it is all these springs and masses, and it's covered with a surface that you can see. Here's also another object. It's a cantilever hanging from a wall. This one is actually the same thing, but not a cantilever object. It's a very interesting way of modeling an object. Simulation efficiency. You need to consider the simulation efficiency. It's measured in spring evaluations per second. And it's actually per real second, not per simulated second. So keep that in mind. You also have typical rates that it's used in Python. You have 10,000 springs per second. In C++, you have 1 million springs per second per CPU core. And in CUDA GPU, you have 1 billion springs per second. And this is for GPUs like RTX 3090, 4000 or more cores. If efficiency is low, you need to keep the structures simple. Okay. Here are more examples of a spring mass simulation. So here you can see the simulation speed for different programs and also languages. As you can see, Python has the lowest simulation speed, while CUDA on a 3090 GPU has the highest simulation speed. So things that we need to keep in mind is that K and DT is tricky. If the structure is too wobbly, then K is too small. If the structure vibrates, K is too high. If the structure explodes, your time step dt or k is too large, and you need to set dt to a set dt to a small step, like 1 to the power of 10 to the power of -5, and like set k to a lower stiffness, like 10,000, and increase them from there. Just start from a stable position and then start changing the variables little by little. Once you get it to work, you can easily parallelize the loop in a 4a, 4b to use all your CPU cores. For example, in C++, use OMP If you are really ambitious, you can even use GPU or CUDA. Be sure to double precision numbers for all your calculations. That's it, guys. So this is for Spring Math Simulation. I'll talk about, you know, a different type of, simulation, and I'll also talk about PyBot in another video. So make sure you follow this channel to make sure you do not miss those videos. And also, if there's another thing you want me to talk about in terms of robotics, uh, let me know in any way possible in the email, chat, whatever is accessible. Take care.